Hi everyone, I'm Rohit Kumar Singh, the TA for this course, Statistical Mechanics, and this is our 10th live session. Um and today, so far we have been discussing the statistical mechanics, and we discussed in the last week we discussed the quantum statistical mechanics. How we saw that instead of a density function, we have a density operator uh, for the quantum statistical mechanics, and once we obtain the density operator, uh, we can basically calculate any expectation value of any function like energy, entropy, and such. So uh, and we also saw a quantum mechanical analog of classical equation of Liouville's, and so the basic the basic quantity that we have to calculate in quantum statistical mechanics was this density operator, and from there we can calculate all the expectation value of all the thermodynamic variable that we are interested in. So today I'll just quickly recap. Uh, Building further on the quantum statistical case, we will consider some quantum mechanical systems, such as you know Fermi gas or boson gas. So a gas made up of fermions or bosons, and we will see how how statistical mechanics can be applied in these systems. Okay, so but first, before moving to those systems, I'll just briefly mention a concept called density of states. So, so what is density of states? So, uh, we saw that if in a canonical ensemble, if you or I mean, yeah, if you have a canonical ensemble, we saw that the probability of finding a system with energy E is proportional to the exponential of this quantity, right? Minus beta E. But what will happen if these energy states are very close together? If they are far apart, it's okay. We have discrete energy states. Now, what happen if these are very close to each other so that we cannot differentiate one from another, right? So, for example, you can differentiate here E1, E2, E3, but that cannot be done here, right? And so we have to consider a range, okay, a range of energy states, and this is where the density of states comes in. So suppose you have uh, yeah. So suppose you have a in a very small interval or range. So let's take E and E plus DE. Okay. So suppose you have E here and then a small interval DE. Okay. Now this D is very small. Okay. So that you cannot differentiate all the energy states in this lying in this interval. So that a very large number of energy states lie, or yeah, if in a small interval, a very large enough of of energy states are there. Okay, so, yeah. Then this we cannot write because we don't know the uh, individual discrete energy levels. So in this case we'll have to consider a probability density, right? So where uh, this is the probability of finding state with energy lying in interval E plus D. Okay, so instead of a probability of giving a single energy state, we now have to consider a probability of finding an energy of finding states with energy lying between this interval, and this will be proportional to the same factor times a quantity dE and then the small interval t. Okay, and this quantity is what we call density of states. Okay, which is basically dn upon de, number of state number of states, and this is the interval energy d. Okay, okay. And similarly, like we did before, we can uh, take the normalization, uh, which is just sum over, or sorry, in this case we'll have the integral from 0 to infinity. So over all the over all the states. Okay, so this is how we can calculate the probability, and again this denominator is will be our partition function. Okay, so this is the concept of density of states. Basically it's a simple concept, but we will need it later. Okay, now let's discuss a system of so let's first discuss you know ideal gases in canonical ensemble, and we will consider cases where this ideal gas is made up of either bosons or fermions. So bosons and fermions, you guys know that bosons are basically spin integral spin, I mean the particles with integral spins. Okay, so for example 0, 1, 2, such that, and fermions are spin half particles. So, So bosons can be photons, okay, pions, etc. Fermions are electrons, sorry, so spin half particles like electrons and yeah, protons, etc. Okay. Yeah. Now, uh, okay, I'll tell more about these later. So just first, let's consider the case of ideal gas. So we know that the canonical ensemble, I mean the partition function here is given by this formula, right? If you have discrete energy states, it is just the sum over all the energy states, right? And now this energy, okay, so for a so this is summed over all the ensembles, right? I mean, and for each ensemble we have this formula, okay. Now I'll explain what is. So this is the total energy, okay, of the system, and this total energy should be equal to uh, sum over uh, energy of a single particle, okay, or you can say yeah, energy of a single particle and the number of state, uh, number of part sorry, so yeah, no, this is not the energy of a single particle, this is the energy of the single particle, I mean energy of the state in which the single particle lies, and this Ne is the number of particles lying in that energy state. So let me write it. So Ne is number of particles in single particle state with energy E, okay. So what you have is, so you have these states, okay, and they all have some energy E, and uh, some number of particles lying in this energy state E, okay. So this is the case, I mean, so we are talking in terms of quantum mechanical ensemble, okay. So here uh, we are talking in terms of energy states basically, okay. Now so this is fine. Also uh, this I mean number of this number of states, single particle states, if we sum it, it should give us the total number of particles, right? This is also understandable, right? Now so we can write this partition function again like e to the power minus beta. So I'm writing in place of energy, total energy E, sum over all the single particle state. Okay, and we can introduce a factor called G, which depends on the number of occupants. Okay, so what it is basically, so this factor, it's called the statistical weight factor. Okay, and this will be 1 for bosons and this will be either 1 or 0. So it will be 1 if for all, number of particles either 0 or 1, or it will be 0 otherwise. So what does it mean is basically, so fermions, you know that due to the Pauli's exclusion principle, uh, fermions cannot, not two identical fermions cannot lie in the same energy states. Okay, so Ne will be either 0 or 1 for fermions. Okay, it cannot be 2, 3 or anything. Okay, so if this is the case, then this summation gives you a 0 value, because we have defined G is equal to 0 otherwise. Okay, so this summation is valid only when Ne is either 0 or 1. Okay, for fermions. So that is why we have added a factor here. And for bosons it is always 1, because uh, since bosons are of integral spin, more than, 2, more than 1, 2, 3, any number of bosons can be accommodated in a single energy state. Okay, okay, so we have this expression of partition function, and it is valid for both bosons and fermions with their particular statistical weight factor G. Now, since we have now the partition function, we can calculate expectation value of almost anything, right? So one important quantity is called the mean occupation number, and it is given by this Ne average. Okay, so what does it mean is, so you have these energy states, and for a particular energy state we want to know what is the mean number of particles that are there. Okay, so what does it mean basically is the what is the most probable value of n. So it is the most probable value of basically Ne. Okay, so this can be calculated by using this averaging formula that we have used earlier, and then divided by this partition function. Okay, so I'm not going in detail into the calculation. I'll just write out the uh, end result. So you will get this. Okay, let me write it here. this is a very important formula. Okay, now here Z is the fugacity that we have seen earlier. And what about A? So A is equal to 1 for fermions, N is equal to -1 for bosons. Okay, so now to understand what does this function looks like, let's try to plot it. Okay, so on y-axis we take this mean occupation number, and on x-axis, so this can be further written as uh, so if you explicitly write the expression of fugacity, we'll get E minus mu over kt plus A, right? So on the x-axis we take this value, so this is simply Ex plus A, okay, where this is x. Now what happened for the fermionic case? So for fermion A is equal to 1, right? So for fermions this is just 1 over Ex plus 1, right? And so let's put some values here. So suppose this is 1, this is 2, 3 and such so on, and suppose here is 0, here is -1, -2, 1, 2, 3, such that. Okay, okay, now for fermions, if E is equal to mu, right, then this term is basically 1, right? And so you have, so let me write here, so Ne is equal to 1 by 2 if E is equal to u, and if E is equal to u, your x is 0, right? So at this value, at this point, mean occupation number is half, and below this point it will decrease like this, right? Okay, like this. It will be an asymptote basically. Now what will be the maximum value in this case? Any idea? Okay, so the maximum will be when E minus mu is basically uh, so the maximum will be when this quantity is 0, right? So and this to be 0, E minus mu over kt should be equal to, I mean should tends to minus infinity, right? And so uh, and this will happen when mu is less than e and t tends to 0, correct? And then we will get uh, maximum occupancy should is equal to 1. So it will tends to 1, it will never be equal to 1, it will always tends to 1. So it will be like this, okay? Is it fine? It will never reach 1 because we cannot reach the absolute temperature 0. And for bosons, so this is for fermions, right? For bosons you have this -1, right? So at e equal to mu or x equal to 0, you get maximum occupancy is equal to -1, right? Now this cannot happen, right? This is not true. I mean, how can be a number? I mean, number of there should be some particles in the energy state E, right? It doesn't make sense to get average value of -1. So this will never happen in case of bosons. Okay. So around at 1, oh sorry, around, so this is the 0. So since E can be never equal to mu, uh, what can happen is you will get closer and closer to I mean x will tends closer and closer to 0, right? Or yeah, and at E equal to mu you will have a shoot up like this. I mean at E tending to mu, okay? And this is what is called the Bose-Einstein condensation. Okay. So this is for basically bosons, and this is for fermions. Oh, sorry. Sorry. Yeah, this. Yeah. At E equal to mu, x is equal to 0. So this this is equal to infinity basically, right? because the denominator becomes 0, so this tends to infinity, and hence we have this suit up here. So and this is called the Bose-Einstein condensation. Okay, so you see that the I mean, since we already assume that since we already had this factor here in the partition function, so that give us the true, the true mean occupancy number, such that this, I mean, it it preserves the basic, physics of these bosons and fermions. So, in case of fermions, the mean occupation number cannot exceed the one. Okay, and this preserve the Pauli's exclusion principle, that none of the energy state can have more than one fermion. Okay, and for bosons we get a state with where the the this occupancy number tends to infinity, right, which is the condition where this Bose-Einstein condensation occurs. Okay, now let's discuss more about this Fermi gas. Okay, this the case of fermions. So if you have now an ideal Fermi gas, okay, we saw that the mean occupation number is given by this formula, plus 1, right? Now if we take this condition of temperature tending toward 0, what will happen? We saw here that it will tends to 1, okay, for energy less than mu, or 0 for energy greater than mu. Okay, and this limiting case where temperature is T0, we call it the mu is called mu 0. Okay, and it is called the Fermi energy basically. So this is the chemical potential, and it is called Fermi energy EF. So we will discuss later what this Fermi energy means. So this means that all single particle states up to energy equal to mu naught are completely filled with one particle each, right? We have one particle if E is less than mu naught, and 0 for E is greater than mu naught, so one particle each, and states with E greater than mu naught are empty, right? So if you plot it, the mean occupation number, you will get a step function, right, like this, and this is your mu naught. So above this you have 0 occupation, and below this you have 1. Okay, now if someone wants to calculate the total number of particles, in this case in the Fermi gas, you can do that by simply integrating over the density of states, right, from 0 to Fermi energy EF. because as I mentioned, so this is just dn over de, right? So it is just the dn, integral of dn. Okay, so this dn is basically, number of particles in an interval e to de, right? So dn is number of fermions here lying in an interval e and e plus de. Okay, now here the density of state, we can write it uh, you know explicitly here. How we can do that? So as I mentioned, this density of state is what it is basically, number of states, right? I mean, different, so number of number of states lying in interval E and DE, which is same as saying the number of fermions, because each state have a single fermion, right? As we saw here. And so we know, and number of, so basically number of states is given by, volume in phase space divided by the unit volume of the phase space, right? I mean the volume of a single state in the phase space, which is just h cube. And the volume in phase space, you know that this is given by d omega, which is nothing but sorry, dq cube q and dq p by h cube. Further, we can write it as, so sorry, uh, this volume integrated over, yeah. So this will give you, if you integrate it, I mean if it is, if your gas is contained in a volume V, you will get V as the volume of the container, and d cube P you can write it as, you can write it in a spherical polar coordinate like this, and a factor of G will be added for the to account for the degeneracy. Okay, so G is basically the degeneracy factor that we saw earlier. So then finally your density of state will be divided by dE, right? And this is a very useful formula to use. So yeah, so you have noticed that we did not integrate it over the momentum space, because so we are calculating the number of states basically in in an interval, right? In the small interval, in a small interval e plus dE, right? And so since we are taking the interval over energy, we have to take in the so this volume in phase space will be also calculated in a small interval of momentum space, right? Because energy is related to momentum in phase space. So that's why we only integrated over the position coordinates, okay? And this momentum space we kept it, we did not integrate it because we need the small interval in momentum, basically, okay? So let me know if you understood this or you have confusion. And we will see how this will I mean help us in our problem later. So this is the expression for density of states for a fermionic ideal Fermi gas, basically. And this can be, generalized for uh, basically all the ideal gases, right? This is true for bosonic gas also, this density of states, because we still have not considered anything about G. So G is different for bosons and fermions that we will consider later, okay? So let me know if you understood till here, then we can go to problems. Is it fine? Should we do some problems? Who is connected? Susmita, are you getting some ideas? Okay. These are have been discussed in the lectures, so I'm just briefly recapping it. So let's do some problems. I don't have much problem for today, but let's do them. Okay, so here this is to understand the degeneracy. What does this G factor means, basically? So suppose there are three identical spin half fermions, okay, and we have to distribute them in two non-degenerate distinct energy levels. So suppose there are two energy levels, E1 and E2, okay, and you have three fermions, okay. So you have three fermions like this, and you have to you know uh, distribute it in these two energy levels. Now how many number of ways that this can be done, that we have to calculate. Now namely, if we forget about the spins here, then this cannot be accommodated in two energy levels, because one will contain one will contain one, as we saw here, right? As we saw where yeah, one state can only accommodate only one fermion, right? But since these have spins, so this might be a spin up, this might be a spin down, this might be a spin up, right? So then two can be accommodated in one energy state with spin up and a spin down, and then the other one can go here, right? Or what can happen is, another configuration that can happen is, one can go here and one spin half, a spin up, a spin down can come here, right? Like this you have different scenario. So this is what the question asks. So how many number of ways that this can be done, okay? So basically we have to calculate the total degeneracy, okay? So total degeneracy is given by number of available energy state times number of degeneracy due to spin. Now, number of degeneracy due to spin we know is 2s plus 1, right? We know this from quantum mechanics. If the spin is half, then number of degeneracy due to spin, which is gs, is equal to 2 into half plus 1, right, which is 2, right? Sorry, yeah, it's okay. Yeah, this is 2. And so total degeneracy given by G is equal to number of available energy state, which is 2, into this degeneracy due to the spin, and so we have 4. And the total number of ways to distribute this 4, I mean basically, to distribute these 3 fermions in 4 uh, 4 non-degenerate states is given by G, C, N. Okay, it's a just we have to take all the combinations. So 4C3, which is equal to 4. Okay, so there are basically 4 ways to distribute them. So two ways I have already here denoted. Other 2 ways can be like, so what can happen is, uh, so out of these 3, 2 can be a spin half, 2 can have a spin down, and 1 can be spin up. So here we have depicted 2 a spin up, 1 a spin down. Or what can happen is 2 can have a spin down like this, and 1 can have a spin up. Now since these are identical, non-distinguishable identical particles, so we don't have to worry which is which is which. Okay, but these 2 cases can be there, right? And so uh, you again have this, sorry, I mean wait, sorry, spin down, spin up, and then spin down. Okay, or spin down, uh, yeah, spin down, spin up, spin down. Okay, so these 4 ways you will have, sorry, these 4 ways you will have. Is it fine? Okay, if you understood it, we can move to the next problem. Should we move? So just remember this formula. Okay, total degeneracy is always equal to number of available energy state times number of degeneracy due to spin, or this degeneracy could be due to other reasons also, like so spin is one case here. Degeneracies can be introduced by different other processes. For fermions, it is due to spin only. Okay, so since electrons have spins, they can be either a spin up or a spin down. So that's why there is a degeneracy, and so that's why we can accommodate 3 electrons or 3 fermions in just only 2 energy levels. Hello. So Smita, are you talking? Okay. So let's move to the next problem. If you don't have any doubt here. Okay. Now here the problem says it's okay. Find the total number of particles in an ideal Fermi gas contained in a volume V with Fermi energy EF. Okay. So the Fermi energy is given. So we know what Fermi energy is, right? We just discussed it. So if the energy of states, I mean, so in an ideal Fermi gas, okay, when you tends when the when you tends to absolute temperature, okay, all the particles below energy Fermi energy, okay, all the states will have uh, occupancy is equal to 1, right? Mean occupancy equal to 1 for this and 0 for this, right? We saw here, we saw earlier this, okay? So this is given, and we have to find the total number of particles. Now total number of particles is basically saying total number of states, right, from 0 to basically EF. I mean, so these states have energy, right? These are single particle states, and this you can write it like density of state times energy interval d, because we know that density of state is dn upon de, right? Is it fine? This we derived earlier also, and we know from our earlier discussion the density of state for a fermion is given by this formula, right? So we can just put this here and try to calculate the density of state. So if you put here, the integral becomes instead of dE we will have dP, right? D get cancelled, so we will have dP, and we can easily integrate it. So these are all constants, so we take them out. 4 pi gb, we have p square dP. Now this integral goes from 0 to EF, and here the integrand is in terms of momentum, okay? So for Fermi energy we have a Fermi momentum also. Okay, and these are these are related by uh, so basically the relation between the energy and momentum, right? E is equal to p square by 2m. Okay, so instead of integrating it from 0 to Fermi energy, we can integrate it from 0 to Fermi momentum. This is fine. So finally we will get 4 pi GV EF cube by 3h cube. So this is the total number of particles in an ideal Fermi gas. Okay, in terms of this Fermi momentum, which is related to Fermi energy by this formula. Okay, is it okay? Anyone has any doubt? Many people are joining late. I don't know uh, if you guys did not know about the session or so. Those who are joining late, if you have any question, you can ask. So what in this particular problem, what I have calculated is, I mean, the question asks the total number of particles in an ideal Fermi gas contained in a volume V with Fermi energy EF, and I just explained that the Fermi energy uh, is that energy below which your occupancy of all the states is 1 and above it occupancy is 0. Okay, and so the number of particles will be just a integral of number of states lying from 0 to Fermi energy EF, because each state will have a single particle occupancy, and then we just use the density I mean sorry we use the energy density expression here, and we calculated the number of particles. Density, this is called the density of states, not the energy density. So I hope you guys understood the concept of density of states from the lectures. I mean, I explained it in the starting of my starting of the session, but many of you were not there. So if you don't understand this density of state, you can ask. I can try to explain it again in few minutes. Okay, or if it is fine, then I can go move on to the next problem. So the next problem is related to this one. Okay, so here it asks us to calculate the ground state energy for the same system, for the system of Fermi gases, and hence the average ground state energy per particle. So what will be the ground state energy? So ground state energy is that energy in which all the states are filled with a single particle, right? From so you have various energy states. All the energy states, since we know that each energy state can have only a single occupancy, all of them are filled from 0 to EF. They are filled with single particles. Okay, and then if you provide some energy, then those who are above EF, one can jump from there and you get excited states. Okay, so this is the definition of ground state energy for a Fermi gas or a system of fermions. And so ground state energy is basically you can integrate it, En dn, okay, from 0 to EF. Where En is the energy of single particle state, and these and since these, I mean, I have drawn these energy state like this, but they are non distinguishable. Okay, these are packed together, so we have to take an interval of uh, you know an interval of energy, right? We have to talk in terms of interval, and so dn is basically number of energy states lying in interval E and E plus DE. Okay, and again we can write it in terms of density of states. So in place of dn we can write this, correct? And we know that E is given by p square by 2m, and density of state we just use this formula, so we get gv 4 pi p square dp, right? D get cancelled over h cube, and this let's take the constants out. So this is integrated from g0 to Fermi momentum, gv 4 pi gv divided by 2m cube e to the power 4 dp. You will get finally uh, is it fine, or yeah, it is fine, 2 pi gv. So and here will be a factor of 5 coming from the integration, and here pf 5, pf to the power 5. This is the energy energy of the ground state. We denote it by E naught. Now the question asks average ground state energy per particle. Okay, so average ground state energy per particle, if you naively think about it, it should be what it should be. You have total energy E, okay, and ground state is basically that state in which all the all the energy state up to energy EF are filled with single particles, okay, and above that there is no occupancy, okay. So you might think naively that maybe the average ground state energy per particle should be equal to EF, but that's not true. Okay, so as you can see, so average ground state energy per particle is basically E naught by n. So this is the number of that we calculated earlier, number of particles, right? And if you divide this by this, you get 3 pf square by 10n. which is equal to basically 3 by 5 EF. Okay, so it is not equal to this Fermi energy but a fraction of this Fermi energy. Okay, so this is very interesting to see. It's a very important result. Is it fine? Anyone has any doubt? You can ask. Okay, so if no one has any doubt, let's move to the next problem. This is the last problem. So yeah, so consider a system of n non-interacting electrons per centimeter cube. Okay, so per centimeter cube you have n non-interacting electrons. Electrons means fermions, right? And each electron can occupy either a bond state with energy. So this is the bond state energy. Okay, if the electron is bonded, it will have a energy minus EB, or a free particle continuum with energy p square by 2n. So this is the case when you have a gas of such particles and they are free to move around. So they will have this energy. Okay, and it is given, it is that it is non-interacting. So we can consider it as ideal system. Now we have to calculate the density of state as a function of E. So in the continuum case only, okay, not in the bond state case, because in the bond state there is no concept of density of states, because we know each state have this energy minus EB, right? And they are distinguishable. But in the continuum, free particle continuum, we have to consider this density of states. So I mean, we have already done this in our earlier problem. So just to highlight that uh, when does the density of state concept comes in. Okay, so we already have this formula for density of states. Okay, and since it is they are electrons, the degeneracy due to the spin is given by this formula, right? V is the volume, and p square is given by 2me. So dp can be written in terms of, because we need as a function of energy, so in terms of energy we are writing everything, right? Is it fine? So what I did is just differentiate both sides, so you get 2p dp is equal to 2mde, to get 2 to cancel, so dp is equal to mde divided by p, and p is what? P is just under root 2me. So finally you get this, and you plug in here the dp, gs, and p square. So if you plug everything in, you will get density of state as this. Okay, so like this you can calculate the density of states of different systems. So if this also this quantity will be here 2, right? Because the spin is half, electrons spin is half, so gs is equal to 2 that we have put here. Is it fine? Okay, I hope everyone understood something. And so if you have no doubt, we can close this session, and if you have any question you can ask. This is the last problem from my side. Many people joined late, so you guys can look at the, I mean this, I'll upload this in on YouTube. You can get the link from the NPTEL website, so you can go and check again if you have some confusion. Okay, so if no one has any question, we can end this session. So thank you all for joining. Bye. Thank you. Bye.